by Professor Bhagwati Prasad from Indian Institute of Science, Bengaluru, India. So I'll give a very brief introduction of Professor Bhagwati Prasad. So he serves as a faculty member and Infosys Young investigator in the Department of Material Engineering at the Indian Institute of Science, Bengaluru. He leads Disruptive Electronic Materials and Nanoelectronics Devices Lab. And the main work that they are doing is of the next generation electronic materials and devices tailored for applications in artificial intelligence, Internet of Things, neuromorphic computing, and quantum technology. He received his PhD from University of Cambridge, and then before that he did his master's at IIT Kanpur. Please welcome Professor Bhagwati Prasad. So the title of his talk is Voltage Control of Magnetism for Ultra-Low Power Spintronics. So Professor Prasad, the floor is yours.
Okay, am I audible?
Yeah.
Great. So somehow the camera of my laptop is not working. Hopefully that should be fine.
Yeah.
Okay, so yeah, I'm sharing my presentation now. Okay. Okay.
Yeah.
Is in full screen now?
Not full screen. I think not in the presentation mode. You need to click the presentation mode.
No.
Right now, yes, it's working perfectly. Yes.
Okay, wait a minute. I think I should share the screen. Okay. What about now? It's all good?
Yeah, it's all good. Yeah.
Perfect. Great. Okay, yeah. So thank you very much for the committee, organizing committee, for this invitation. So it's my pleasure to give a talk about our recent work on voltage, on voltage control of magnetism for ultra-low power spintronics. So I'm Bhagwati Prasad. I'm from ISC Bangalore. Okay. So yeah. So let me little bit tell about our group and institute. So yeah, I mean, we are one of the kind of oldest institute in India, around more than 100 years old institute, and C.V. Raman was our former director. So our institute focuses on the fundamental research mostly of cutting edge science, and nowadays we are doing a lot of technological stuff as well. So yeah, it's in southern part of the India in a Karnataka state. This is my group photo. So in my group, we work on various disruptive electronic materials and electronic devices. We work on materials, 2D materials, metal oxides. We grow by them by PLD, sputtering, mechanical exfoliation. Then we make various, devices like test vehicle devices. We use the physics and the physics of ferroelectricity, ferromagnetism, magnetoelectric, piezoelectric, and eventually we make some sort of technology or devices for neuromorphic computing, in memory computing, or non-volatile memory. So before I start my talk, I would like to acknowledge the group member, my group member who has worked in this project, and also a collaborator from Western Digital and from other places, from UC Berkeley and from Taiwan. And then also various funding agency. So without this funding agency, we could not do what I'm going to show today. Okay, so we all know that we are going through a wave of AI, generative AI, and for that, if you look in the background to run those, and especially to run the data between the processor and your memory, you need a different kind of hardware, which is basically more efficient hardware than what we have at this moment. And so in our current computational architecture, which is called the von Neumann architecture, which is basically kind of, if you look in this pyramid, at the top of this pyramid, we have processor, and at the bottom, we have a cloud storage, and then there's a flash drive, and then there's a DRAM. So when you go from top to bottom, what you see that this speed is decreasing, and your capacity is increasing. And on the top of that, the blue one are volatile, and the gray one non-volatile. So you permanently store the data in the non-volatile memory. And so whenever you need to access the data, you need to actually, your processor need to come here and do that. So this is, especially in today's world, AI world, where we need to making a lot of synthetic data rather than real data. And for synthetic data, you have to come to the memory all the time because you need to get a lot of data from there and to process that. So our current computational architecture is not really supporting that, and to do, like to do this kind of things at this moment, people are kind of making something called high bandwidth memory, where you put your processor and your memory on the same chip, but that consume a lot of power. So we need to find a different way of doing these things. So that's actually one of the burning issue at this moment. And at the same time, storage is another important concern, that since we're generating lots of data every time, we need to figure out how to store this data permanently at low price. So people are exploring various novel way of storing data, including the DNA storage. Okay, so in terms of memory part, if you look, and even a storage part across the globe, people have been looking for last few years many different technologies. That includes spintronics based technology like spin orbit torque, spin transfer torque, voltage control magnetic and isotopic based MTG, then various ferroelectric based systems like ferroelectric capacitors, ferroelectric field effect transistors, and ferroelectric junctions. Then also a lot of work has been done in resistive RAM area, and many other new interesting like stuff people have been trying. And in addition to this, for archival memory, as I told, that DNA storage is being explored vigorously. So a lot of things has been happening in this area for last 2 decades, and at this last 2 3 years, a lot of tension has come to this memory side because of the AI. So we also have been working on these things for last, this is basically my work at different places for last 8 10 years. This key work, not everything what we have been doing, but it's more on the memory technology side. So I have developed, we have developed a magnetoelectric spin orbit logic, a new completely new logic system, MISO, with the Intel team. In fact, this technology is right now under the kind of technological evaluation at Intel. Then we have also developed, demonstrated how one can switch the magnet with the electric field, and that is also very low power consuming device. Basically, you need in terms of the energy, you need around 1 to 10 autojoule energy to operate 1 bit. So we have looked at various interesting material system, including multiferroics, lanthanum doped bismuth iron oxide system, which actually give us some sort of platform where you can control the magnetism with electric field. Then we have been also working on voltage control mechanisms, including voltage control magnetic anisotropy, and some of these things I'm going to talk today. And then also some sort of neuromorphic computing, where we shown how one can pattern the functional liquid, and you can actually integrate them with the interesting electronic devices. And also we have been also working on ferroelectric memories, that includes ferroelectric tunnel junction, ferroelectric field effect transistors. And also we are also making some sort of new interesting innovative spin cloning devices, which is basically spin filter tunnel junctions or other interesting novel tunnel junction devices. Okay, so what you see that this is a nice, interesting review article, and even review and perspective article, which tell that the kind of the potential of the spin-based technology or a non-volatile memory technology for kind of developing a full spin-based memory logic system. So if one can really make all these things working in a synchronized fashion, then you can completely replace the logic and memory of the current computational architecture and make something of full spin based technology out of that. Okay, so that tells that there's a lot of potential in the spintronics, and if somehow we can manage to make this technology energy efficient, then there's a huge opportunity. So if you look the current computational architecture, in current spin-toning devices, the MRAM, spin transfer torque based MRAM, is the one which is basically at the forefront of the technological innovation. So in fact, some of the products are already being commercialized by the company Everspin, another company, and so they use something called the spin transfer torque to switch the magnet there. So in this case, what you do is basically you flow this current, and the current get spin polarized from the fixed layer, and then it runs through the barrier, and then it can transfer the spin angular momentum to the free layer, and that way you can modulate the magnetic configuration of the free layer. But especially when you make a smaller devices, you have to increase the anisotropy because you need to get the higher tension. If you increase the anisotropy, and then you basically your switching current is proportional to the your anisotropy field. That means switching current does increase with the decreasing the size if you increase the anisotropy. And if you do that, then actually it's create the like this joule heating effect because you are consuming a lot of power. Okay, so how to solve that problem is people have been exploring various other techniques. One of the very well explored one is a spin orbit torque, where you flow the current through a heavy metal. Then, due to the spin Hall effect, this charge current can be converted into spin current, and the spin current can actually switch the ferromagnetic layer, which is just adjacent to the your heavy metal, and that way you can also switch the this MTJ, the resistance state of this MTJ device. But we need a material which shows very high spin Hall angle, and also at the same time we need a material which shows very good conductivity, so that you flow decent amount of current and you can actually achieve what you want to achieve. But so far we don't have such a magic material yet, which can lead to make a robust technology. So what are the other opportunities? One of the way is that can you not switch the magnet rather than current? Can you not switch the magnet with the electric field? And this is what I'm going to talk today. So if you use a current-driven spin transporter switching, the energy requirement comes around 10 femtojoule for operating 1 bit. But if you make a technology based on the magnetoelectric, then the energy requirement reduced to 1 autojoule. So it's a big gain in terms of the energy consumption. So what we can do if we manage to make it happen, then you can see that compared to the various technology, including the MRAM, other MRAM technology like STT, SOT, the magnetoelectric RAM in pretty much in all aspects shows the better performance, in terms of endurance, read time, write time, cell size, all looks very lucrative. So basically, if you can make this working, this is going to be the final solution, big, energy efficient solution for, especially for this ongoing need of solving this memory wall issue. Okay, so what we need to do, we need to basically switch the magnetism with electric field. So either you switch the magnetic anisotropy, coercivity, magnetization, exchange bias, magnetic resistance, or Q temperature. So that means in one polarity of electric field, you have one of these magnetic state, and then you change the polarity, then you may get different magnetic state. And that magnetic state, if you somehow manage to incorporate into device, and then you manage to actually get a two different resistance state, then you can use this for some sort of memory applications. So this is what we have been trying for last few years. So in our group, we have been doing various ways of voltage control of magnetisms. So I'm talking about these three ways. One is a voltage control magnetic anisotropy, other is the voltage control exchange coupling, and then third is a multiferroic based magnetoelectric coupling. Let me talk about them one by one. So first, the voltage control magnetic anisotropy. So in a voltage control magnetic anisotropy, what you do? Basically, if you make a perpendicular MTJ, magnetic tunnel junction, at the interface, you basically have interfacial perpendicular magnetic anisotropy, and because of that, your EG axis is in outer plane. So you have a perpendicular magnetic anisotropy that's coming from the interface between the cobalt ion boron and NGO. So if you apply electric field, that means you drop some sort of electric field across the interface, and that electric field can modulate the electron occupancy of this d orbitals, which is and hence it can actually modify your magnetic anisotropy. So if you can manipulate this magnetic anisotropy with the voltage, then you can use this for basically MRAM technology. So how exactly it works? For one polarity of the voltage, you increase the PMA, and hence you don't do anything. But for other polarity of voltage, you decrease the PMA. So when you decrease the PMA, if you apply small in-plane magnetic field, then your spin will start precessing around the in-plane magnetic field. And then if you time your voltage very nicely, precisely, then you may get both state up and down. So that way you can basically get the state up and down. But the problem is that now we are more dependent upon the timing of the voltage pulse, that how far you apply the voltage pulse, how long is the voltage pulse. And that has actually created a problem for deterministic switching. So one of the problem of the VCM is that how to achieve deterministic switching. However, still the problem, still one of the concerns is that how you increase the VCMA coefficient itself. So we try to, so especially why we need a higher VCMA coefficient, because if you really want to make smaller devices, then in that case, as I told that to get the higher attention, you need to get higher PMA. And all, so if you need to get higher PMA, then you also need to have a higher VCMA effect, because the delta will increase. When delta will increase, then your VCMA coefficient has to be increased. So eventually, you need a higher VCMA coefficient, especially more than 100 femtojoule per voltmeter to make something working at low, at lower technology node side. Okay, so we have done some ab initio calculations, and we found that when you introduce a thin, heavy layer of the heavy metals like iridium, platinum, other things at the interface between the cobalt and boron and MgO, you can actually modify the interfacial anisotropy. In fact, you can increase the PMA and even VCMA as well. And this is what we have done some experiments. So we introduce a thin layer of the iridium. We have done many experiments: iridium, magnesium, aluminum, platinum. So in this today, I'm showing only iridium work. So we introduce a thin layer of iridium between the cobalt and boron and MgO, and we make some sort of Hall structure with that. And then we basically have done some experiment with the post-deposition annealing experiment, basically, to check that at what temperature you get the highest VCMA and PMA. What we found that typically people use around 335 to 350 degrees centigrade for annealing this MRAM stack. But what we found that 335 degree, the iridium diffuse inside your ferromagnetic metal, and hence you lose the magnetization. And because of that, your Ki goes down. And also you don't get very high VCMA. So best is that you reduce your temperature. So we optimize this annealing temperature. We found that 310 degrees centigrade is the right. With the optimum thickness of the iridium, you can get the high VCMA coefficient as well as high PMA. So this is the PMA part. And then we also did the VCMA measurement. For that, we basically make Hall device, and we have measured the Hall resistance for the different gate voltage. So we apply the gate voltage across this, and we measure the Hall resistance, and then we basically extract this part where we apply the gate voltage minus 1.5 volt to plus 1.5 volt. You can see that how the resistance is changing here with applying the gate voltage, and you can fit with the Stoner-Wolfert model, and from that you can get the HK versus the gate voltage, and then from that you can calculate the VCMA coefficient. So we got the highest VCMA coefficient for the stack, which was annealed at 310 degrees centigrade with a higher PMA. So that gives some sort of conclusion that you need to find the right annealing temperature, right insertion layer. One can increase the PMA and VCMA. We have been doing a lot of other insertions and a lot of other interesting stuff. But only so far this work has been published. So that's why I'm showing only this work today. So we also cross-check with our Hall bar devices performance with the MRAM. We found that the VCMA coefficient that you get from Hall bar devices that pretty much come close to what you get from the MRAM stack. So whatever we're getting in the Hall bar devices, that can be translated to the MRAM structure. Okay, second one is the voltage control interlayer exchange coupling. So as we told in the VCMA part, what happens is that when you apply voltage, for one polarity of voltage, you increase the PMA, and for other, you decrease the PMA. Okay, but so this is not deterministic in nature, and hence this creates a problem. So we recently come up with a new way of doing this voltage control switching, which is called a voltage control exchange coupling. So you know that there's RKKY coupling between the two ferromagnetic metal when you put a non-magnetic metallic spacer between the two ferromagnetic. And so what we found that with electric field, you can actually change this RKKY coupling. Okay, so ideally what you should do that, this is how the RKKY coupling look like when you change the thickness of this metal layer between the two ferromagnet, and this is how it look like. So if you somehow modify the electronic states at the interface or at the Fermi level, then you can go from parallel to the anti-parallel configuration between these two layers. And this is exactly what we have done. So we put the iridium as a spacer layer between the two ferromagnetic layers, and then we systematically vary the thickness from 7.5 angstrom to all the way 15 angstrom. We get nice RKKY kind of oscillation, and then we basically optimize the thickness of the iridium, which is close to where you can go easily from anti-ferromagnetic to ferromagnetic coupling. And then there we apply the gate voltage. And we found that with applying the gate voltage, you can modulate this interlayer exchange coupling. And this is what we found. For the very first time, we demonstrated that with the MgO barrier, one can modulate the interlayer exchange coupling, and the the VCEC coefficient is not that high, but it is kind of the proof of concept that yes, this does work. So eventually, if we can make this working with higher VCEC coefficient, around 100 or 200 femtojoule per voltmeter, then one can actually integrate this with STT. VCMA you can't integrate the STT, but this one you can. So with that, you can reduce the STT switching. So basically, this can assist for SST to switching at lower current, and that way it can actually work for low dimension devices. Because as I told that one of the problem is that you need a higher current to switch the devices at lower CD, and that creates a joule hitting effect. But if you incorporate ECC with that, then that is possible. Mechanism, second one. Now, third one is the multiferroic base magnetoelectric coupling. Okay, so here, I'm introducing a material called magnetoelectric multiferroics, which is bismuth iron oxide, BFO. Bismuth iron oxide has a two ferroic orders. It is basically ferroelectric and it is also antiferromagnetic. So it's a G-type antiferromagnet, and it is ferroelectric with the polarizations around 90 microcoulomb per centimeter square, and its polarization is actually, the polarization vector is in 111 direction. Okay, so when you basically map, when you apply the electric field and you map the ferroelectric polarizations, what you see that there's a domain. Basically, this is a ferroelectric domain. Okay, and then you also map the antiferromagnetic domain by XLD PIM. What we see that there's a one-to-one correlation between the ferroelectric and antiferromagnetic domain. Interestingly, when you put a ferromagnet on the top of this, like for example, cobalt iron, this ferromagnet does mimic exactly the domain what you see in here XMLD PIM. And then when you apply the electric field, you can basically pole them, and then you can switch them from white to black with electric field. Okay, so we have actually make some sort of spin ball on the top of that GMR stack. And with the GMR stack, basically what we found that when we so I directly come to here. So when you here we have used a length of the BFO, we make a GMR stack on the top of that, which is basically a spin ball where you have a copper, coffee, cobalt iron, copper, cobalt iron, and platinum. Both have the same thickness, 2.5 nanometer. The bottom cobalt iron here is actually coupled with the LBFO, and hence because of exchange coupling, the coercivity has gone up, as well as there is RKKY coupling certainly. So what happens is that when you apply electric field, you can basically modulate this coupling strength. Okay, so you can go from anti-parallel to the parallel state like that. And in fact, when we can also achieve this state change from parallel to anti-parallel state change of these two ferromagnetic layer just with the voltage. So you apply voltage, you can go from this state to that state. Okay, so this is just demonstrating that you can actually switch the GMR stack with the electric field. You don't need any magnetic field in this case, and you can get the pretty much same GMR percentage what you got here, around, you see, around 1.2%. Okay, so you can achieve that without changing without actually any magnetic field. Okay, then we have further demonstrated that how one can actually, if you reduce the thickness of your LBFO, which is lengthened of the BFO around 20 nanometer, and then what we have done here, we put the platinum cobalt iron platinum coffee, which is around 2 nanometers here. Okay, we put this on the top of that, and we apply electric field. What we see that when you have apply a 500 millivolt positive, then you see most of the domains are white. And when you apply the negative 500 millivolt, then you can go from white to black. So basically, you just with the electric field, you can manipulate these magnetizations from one state to other state without any magnetic field. And so here we have done systematic study from 50 nanometer all the way down to 20 nanometer. And we have shown that how we can actually decrease the thickness of the LBFO, you can decrease the switching voltage. So the switching voltage is more important for engineers where they more concerned about voltage more than the electric field. So if you reduce this voltage below 500 millivolt, then that's actually would be the game changer. So recently we have done more work on that, and we reduce the thickness of this LBFO all the way down to 10 nanometer. And there we could switch this magnet or with this GMR stack with the 250 millivolt. And if you convert that in terms of autojoule per bit operation, it comes around 5 autojoule. So we have already achieved 5 autojoule per bit operations of these devices with this magnetoelectric switching. Okay, so then we further demonstrated that how one can actually make something called the magnetoelectric spin orbit logic. So the idea is that we have magnetoelectric one side, spin orbit other side. And so we basically write with the voltage and then we read with the voltage. So in between, you basically store the data in terms of the spin. Okay. And so this is a new, complete new device we demonstrated, which is called the magnetoelectric spin orbit logic. And then we have published several papers based on that. Okay, so this is a summary of my talk. I have shown that by inserting the thin iridium layer between the ferromagnet and the MgO layer, one can modulate the PMA of the cobalt iron boron layer with applied voltage. We have also demonstrated that one can actually switch the voltage control interreactance coupling, basically, or you can actually modulate the interreactance coupling with the voltage in a magnetic heterostructure where we use iridium as a special layer between the two PMA layer. And then we have shown that when you doped BFO with the lanthanum, you can actually switch the spin ball with just with the electric field, and then corresponding energy requirements is that comes in autojoule per bit operation. And so what I can say that by and large, these three distinct voltage control magnetic effects. So the promising solution for ultra-low power spintronics for realizing high density memory architecture. With that, thank you very much for your attention. And I'm happy to take any question that you have. I think we have a good amount of time for questions. Yeah.
Yes. So thank you, Professor Bhagwati Prasad. So we have a question from Nivedita. Yes, Nivedita.
It was a wonderful talk, Professor. My question is, in case of like VCME, how about for magnetic layer, if we use like giant magnetostrictive materials, how would it change? Like, wouldn't it be like more? Wouldn't it actually be better?
So this is a different physics actually. When you have magnetostrictive materials is basically like one which has higher magnetostriction. They will change their magnetic anisotropy by changing the dimension. Okay. So that more depend upon how you change the dimension. And that typically happens when you put them on the top of some piezoelectric substrate. And you apply electric field, you change their basically you create some strain or compressive or tensile strain, and you can change the magnetic anisotropy. Here's the mechanism is different. It's actually interfacial perpendicular magnetic anisotropy that we are changing. So it's basically happening when you modulating the electron accumulations or electron charge carrier density at the interface. Okay, and that will actually modifying the interfacial density of states. Now, if you use a magnetostrictive material or anything else, it doesn't matter as long as it's actually fitting within the PMA range that we can actually able to change. So I think magnetostrictive materials role will not be that much here in terms of its magnetostrictive property. But it's only magnetic property that which we can modulate with this with the changing the electron occupancy at the interface. Yeah, that definitely will modify it, but nothing to do with the magnetostriction here. Yeah.
Thank you. Thank you.
Yes, Nuno, you can unmute and ask.
Thank you. Thank you again, Professor Bhagwati, for being one of the invited speakers for the APAC region and giving your talk during this session. And I wanted to ask you about the motivation of the high current in lower devices. To my knowledge, as the device gets reduced a lot, sub 10 nanometer, the resistance kind of goes very high. And so the current will go lower as well. So I know that the people usually say that the current that we need increases a lot as the device goes lower in diameter. But what I see is that the current goes way smaller, but the voltage goes high, of course.
Okay, good question. So very good question. So this is not the current actually. At the end, it's current density, am I right? Current per unit area, because that is the one which makes the difference. So ideally, we don't say current density because we say current, am I right? Because that's why it sometimes makes life easy to understand. So it's the current density, and when you make a smaller, that's actually a big problem of all these TMR devices. I mean, one is that TMR is not high enough. That's the intrinsic problem. But second is that when you reduce the size, you have to increase the HK, because you know this anisotropy is depending is
Mhm.
KV. It's K is the anisotropy constant, V is the your volume. When your volume decrease, your anisotropy will decrease, anisotropy energy will decrease.
Yeah.
So to increase this anisotropy energy, you have to increase K. So K means you have to increase HK. HK is an isotropy field. When you increase the HK, your delta, this the barrier, or your barrier will increase, delta will increase, and hence your JC, the switching, which is called a JC, current density, right? Switching current density, critical switching current density, JC. JC is proportional to your HK. So higher would be the HK, higher would be GC, because you have to actually cross the barrier. You need a more energy. And so in that way, you need a higher JC. And a higher JC means you basically now burning your device, actually. You're losing a lot of energy there.
Yeah.
To warming up. It's joule heating, nothing else. Yeah.
Mhm. So yes, I understand your point. So during my PhD, I worked in sub-10 nanometer MTJs. So I can comment a bit on that. And I was using something called chip anisotropy MTJ, which uses the chip anisotropy if you increase the aspect ratio a lot. So in that case, HK is very small, and we are
Exactly.
actually increasing the thickness while reducing the diameter. So in that case,
Yeah,
we
so
saw
this
that
is
the
the
joule
clever way. You
heating,
found the clever way of how to reduce the HK. Yeah. Yeah.
but
So
at the Hoku, they were using laminations of MGO. I think you are familiar with the work of Nishioka, also Junte Garasi, Buchirin and of course the group of Sunsuke Fukami. So putting a lot
yeah.
of MGO increases HK by PMA, just stacking PMA on top of each other. I don't remember, or at least I didn't say, that the joule heating was crazy high. But what I know happens is that the figure of merit for the STT, so delta over IC naught, is very, very high, much larger than normal perpendicular MTJs. So I was wondering if this is also true for this kind of devices that you are presenting, the figure of merit.
Yeah, so I'm talking more on the, I like it. Great. Thank you very much for bringing all this attention. I mean, this is a good discussion points where we used to discuss a lot of things, and there are pro and cons of everything, am I right? It's
Of
not
course,
that
yes.
it's not a black and white. It's all like you have to
Mhm.
go in depth and discuss everything. Is like many things, you know. It's like you
Of
have to
course.
now not only talk about this. You have to talk about when you make an array. In an array, when
Yeah.
you know what happens, the pitch, and then read disturbs and other things come in the picture. So you can actually in one single device you can find a very nice, beautiful, optimized conditions. But when you make an array, and then when you make a pitch very close, device one close to another, okay, because aim is that we make a small device, reduce the pitch size, make them very dense and all that things. But if you make entire stack, then eventually many things you need to think about, right? Not only just
Of
few
course.
things, and there's a collective things. It's not just one thing. So that's one. Second is that, yeah, you said that how, so VCMA and voltage control things are interesting. I think VCMA is one of the problem of the VCMA is that it's not deterministic in nature. That's it's an inherent problem. Second is that the VCMA coefficient is not high yet. From research, people have shown sometimes 300 femtojoule also few stacks. But
Sure.
when you make a real 6-inch or 8-inch, 12-inch wafer and make this thing working, it doesn't give that high VCMA. I mean, I have developed technology in Western Digital,
Yeah.
so it is not going to work that easily. So that's one. The second, the VCMA coefficient is not very high. This VCEC is the new thing which we just published paper last year. I think people will work more on that. This is one of the first work actually in that area. People have done similar kind of things with ionic liquid, but ionic liquid is very slow. So we have done with the MgO barrier. So I hope that a few people have published recently some good papers on that direction. So this could be interesting aspects actually, rather than switching, like changing the PMA. You best just change this RKKY coupling. And if you do that,
Yeah.
then that way you can actually combine with the STT, and that may give some good opportunity. So I would say that, see, this AI and all these things coming in, right? So memory is going to become very hot topic in another 10-15 years, and I think MRAM will survive and will may flourish. Actually,
sure.
this is a good time. Yeah.
Thank you very much.
Thanks a lot. Yeah, it's a good discussion. Yeah.
Any more questions from the participants? Okay. You can write in chat box also. So Professor Prasad, I have a question. Last week I attended Professor Luis Yuzo from Spain, I guess, his talk in Cambridge, and he showed some of the BFO, and in the initial slides you show some of the images.
Mhm.
BFO and he was talking about like it's very much tough to fabricate a ferromagnet on top of BFO because of you need some sort of exact this ferroelectric domains. Is it means from the
Uh,
fabrication point of view?
Not really, no, no. So see, I mean,
Okay.
it depends what you're looking for. If you want to do exotic science nature paper, of course, you will do all those nitty-gritty thing details, right? You will try to map the domain with the domain and do which direction of the domain, all those things. But when you
Hmm.
develop technology, you don't care about many small details in terms of science part. Of course, you take
Okay.
care of the details of the technology part, like when you happens, then how it happens, integration things and other things.
Okay.
I don't think that that is a big problem. I think more than that, the problem is the in general integration. Okay, so in general
Mhm.
integration of the oxide of the metal on the top of the oxide is not very great actually. So especially these ferroelectric materials has something called the fatigue issue. So when you switch this VFO multiple times back and forth, it creates some sort of fatigue and doesn't switch. And then more than the fatigue mostly happen because of the if you use oxide metal electrode, and because of that these oxygen they pile up at the interface, and then
Okay.
they create some sort of barriers at the interface, Schottky barriers, and that creates problem. So there are other challenging things which is more of the integration challenge. So there is a company called the Kepler Computing. They are doing some more things in ferroelectric memory on this direction. So a lot of
Mhm.
progress, interesting direction is going on the background, which I suppose to not tell here. Yeah, but yeah,
Okay.
it is. It's you will see some great things going to happen in next few years. Yeah.
Okay. Okay. Uh, so with this, I think we conclude this session. Thank you, Professor Bhagwati Prasad, for the nice
Thank you very much. Yeah.
talk.
Thanks a lot.